welcome to today's deep dive. I want you to just try to imagine designing a facility back in 1924.
Oh, wow, yeah.
Yeah.
That's a totally different world.
Right. I mean,
Yeah.
there's no computer modeling, no sensor interlocks, definitely no computational fluid dynamics to calculate, vapor dispersion.
None of that. You're flying blind, essentially.
Exactly. You are essentially building a small-scale gasoline refinery, right? And it's staffed by human operators who are manually moving textiles around. And this is happening right in the middle of a commercial shopping district.
Which is just wild to think about today.
It is wild. The risk of a catastrophic vapor ignition, I mean, it wasn't just some statistical possibility back then. It was practically an inevitability. So today we are looking at the rule book that actually stopped those explosions.
Yeah, and that rule book has really transformed into one of the most complex, granular texts in industrial architecture today.
Oh, absolutely.
We are, of course, looking at the NFPA 32, the standard for dry cleaning facilities, and specifically, we're tracking its evolution culminating in the 2021 edition.
Right. But for the engineers listening, the ones actually tasked with designing these controlled chemical environments, we are not going to just sit here and read you mathematical tables.
No, that would be brutal.
Yeah, I mean, if you're drawing the blueprints, you already have the charts, right?
Yeah.
You know how to size a pipe or look up an exhaust ventilation rate.
Exactly. You don't need us for that.
What is arguably way more vital to your facility design is understanding the DNA of this standard. So our mission today is to look at how the rules of dry cleaning safety evolved over a century.
And, the structural philosophy behind those codes.
Right, and how modern engineering is actually being rewarded by the current iterations of the text. Okay, let's unpack this. Because before you even look at the plumbing or the chemical storage, you really have to understand the foundational reality of what an NFPA standard is legally.
And maybe more importantly, what it is not.
Yeah.
Because there is this persistent misconception among even seasoned professionals regarding the actual authority of the National Fire Protection Association.
Right. People think it's like a government law outright.
Exactly. But the NFPA develops these standards through an ANSI-approved consensus process.
An ANSI-approved consensus process.
Yeah. So they bring together these volunteers from highly varied viewpoints. You've got industry representatives, safety regulators, equipment manufacturers, insurance underwriters.
Okay, so it's a big mix of people.
A huge mix. They all sit at a table to argue over fire and safety issues, and the NFPA just administers that process. They establish the rules to ensure the debate is fair.
Right. They're basically the referees.
Exactly. But, and this is huge, the foundational text of the standard explicitly states that the NFPA itself does not independently test, evaluate, or verify the accuracy of any information in the standard.
I want to pause on that for a second,
Yeah.
because it is a massive paradigm shift if you haven't actually read the legal disclaimers at the front of the book.
Most people skip right past them.
Oh, 100%. Yeah. But the NFPA does not independently test the safety claims. They are basically acting as a publisher for a high-stakes, open-source engineering project.
Mm-hmm. That's a great way to put it.
I mean, it's like a recipe book, right? They wrote the recipe for a safe facility. They moderated the debate over the ingredients, but they're not coming to your kitchen to check the math.
No, they're not.
And they definitely didn't build a test facility themselves to see if the parameters actually hold up to failure.
The legal disclaimers in the 2021 edition make this abundantly clear. They disclaim all liability for any personal injury, property damage, or really any damages resulting from the publication or use of their standards.
Wow. Zero liability.
Zero. They state explicitly that they make no guarantee or warranty as to the accuracy or completeness of the information. Furthermore, they don't police or enforce compliance.
So they don't list, certify, or inspect products or installations either.
Nope, none of that.
Okay, this raises an important question then. If they take zero legal liability when a facility fails, and they don't even physically test the claims, why on earth should an engineer treat this document as the ultimate authority? If I'm designing a plant, why am I letting an untested consensus document dictate my entire architectural layout?
Well, it comes down to a legal mechanism called adoption by reference.
Okay, what does that mean?
So the standard itself has no legal teeth on its own. Like we said, it is just a highly detailed white paper. But it gains its teeth when a federal, state, or local authority, what they call the authority having jurisdiction, or AHJ, adopts it into law.
Oh, I see.
When a local building department or state fire marshal writes their municipal code, they aren't equipped to invent new dry cleaning safety rules from scratch,
No,
right?
of course not. They don't have the time or budget for that.
Exactly. So they write a statute stating that dry cleaning facilities within their jurisdiction must comply with NFPA 32.
Ah, so the local government weaponizes the standard.
They absolutely do. But that creates a pretty profound philosophical and legal reality for you, the engineer.
Because the liability shifts.
Precisely. Because the NFPA disclaims liability, the burden of safety falls squarely on independent judgment. The text explicitly tells anyone using the document that they should rely on their own independent judgment or, seek the advice of a competent professional.
And if you are the engineer signing off on the CAD files, you are that competent professional.
You are on the hook.
Right. You cannot stand in front of an investigative board after a vapor incident and say, well, that's what the book said.
Yo, that won't hold up.
Because the book told you to use your brain. You have to apply a century of historical risk management to your specific, unique facility constraints.
And that liability means a comprehensive understanding of the code's intent is absolutely critical. You aren't just blindly following a ventilation requirement. You need to know exactly why that ventilation requirement exists in the first place.
Yeah, you have to know the history of the hazard.
Right. And the challenge is really compounded by the fact that the standard is a living document. I mean, you can't just download the 2021 PDF, lock it in your reference folder, and just design facilities based on it for the next decade.
No, because the text is full of warnings about tentative interim amendments, TIAs, and errata.
Yes.
And an engineer tracking these knows errata are basically just the corrections of errors, typos, or accidental omissions that could, materially change the engineering math.
Right. Just housekeeping stuff, mostly.
But the TIAs are where the real risk management lies.
Absolutely. Tentative interim amendments are changes issued between the regular revision cycles.
Because things move too fast for a 5-year cycle.
Exactly. They are triggered because a new urgent hazard has been identified or maybe a critical new technology has emerged that the current candidate just doesn't cover safely.
So checking the codes and standards section on the NFPA website isn't just some administrative chore. It is mandatory risk management.
It really is.
You have to know if a TIA was issued, like yesterday, that completely alters the required safety interlocks for a specific solvent class you're specifying today.
Because the consensus machine never actually stops. The participants in the NFPA process are constantly considering new information on incidents, chemical behaviors, and innovations.
Every time a plant blows up or a new chemical hits the market, they're back at the table.
Right. Every single time there is an unforeseen industrial failure, the committee starts evaluating.
And the pace of that evaluation is staggering when you look at the historical timeline.
Oh, it's fascinating.
Right. To understand why modern facility design is so intricate and why we have these complex matrices of equipment versions intersecting with solvent classes, we really have to look at the explosive history of the industry itself.
Literally explosive.
Literally. The foundational text notes that NFPA 32 originated in 1924, and the first edition was adopted in 1925.
And if we connect this to the bigger picture, the origin point is super telling.
Oh, so?
It wasn't prepared by a committee focused on textiles or commercial laundry. It was originally prepared by the Committee on Flammable Liquids in cooperation with the National Association of Dyers and Cleaners.
Wow. So they viewed it purely as a highly hazardous chemical processing operation.
Completely. I mean, in the 1920s, the primary solvents were raw, highly combustible petroleum distillates.
It's like basically washing clothes in gasoline.
Pretty much. Things closely related to gasoline and kerosene, the flash points were just terrifyingly low.
Right, any little spark.
Exactly. Facility design at that time was largely about trying to mitigate the inevitable presence of explosive vapors in the exact same room where sparking electrical motors and static generating textiles were operating.
Which sounds like a nightmare. And the timeline of revisions reads like a map of 20th century industrial progress. Following that 1925 adoption, you see amendments hit in 1927. Then complete overhauls in 1936, 1944, and 1956.
Yeah, those were big years.
You can clearly see the engineering response to the chemical boom of World War II in that 1944 revision.
Oh, World War II forced a massive shift in chemical manufacturing. The industry began moving away from the extreme flammability of those early petroleum solvents towards synthetic halocarbons.
And that's when POOC comes in, right? Perchloroethylene.
Exactly. PERC was a massive breakthrough because it is non-flammable. You literally couldn't ignite it if you tried.
Wow, so the immediate fire hazard just drops to zero.
It dropped precipitously, but, and this is a big but,
Yeah.
it introduced an entirely new set of engineering constraints.
Because it's toxic.
Right. PERC might not blow up, but it is highly toxic, and its vapor is significantly heavier than air.
Ah, so that changes the fluid dynamics of the entire facility.
Completely. Think about it. If you are designing ventilation for a lighter petroleum solvent, the vapors might disperse upward, or mix readily with the air.
So you vent it through the roof.
Right. But with PERC, the vapor pools on the floor. It flows like water into drains, into trenches, down into basements.
Oh, man. So suddenly, facility engineers had to design floor-level sweep ventilation systems and entirely different containment strategies.
Exactly. The hazard shifted from thermal ignition to respiratory toxicity and groundwater contamination.
Which perfectly explains the massive overhauls in 1970, 1974, and 1979.
The chemical industry was just churning out new synthetic solvents in the 70s.
And the standard had to constantly adapt to wildly different physical properties.
Yeah.
Like some solvents were flammable, some were toxic, some were both.
It was a very reactive period for the standard.
But then things seemed to slow down. You see minor amendments in 1985, it gets reconfirmed in 1990, minor changes in 1996. It looks like the industry hit this plateau of stability.
A plateau that ended very abruptly at the turn of the millennium.
What happened?
Well, the environmental and health regulations surrounding legacy solvents like PERC tightened drastically worldwide.
Right, the EPA really started cracking down.
Big time. Facility owners were under massive pressure to move to alternative, often proprietary hydrocarbon or silicone-based solvents.
And that forced the engineering crisis that the 2000 to 2007 revisions had to solve.
Yeah, the 2000 edition really had to reset the board. It took all the general requirements for all plants and moved them to the front of the book, establishing a new baseline.
But the real obsession of the 2000 and 2004 editions was addressing this concept of machine conversion.
Oh, machine conversion is just a logistical nightmare for an engineer.
Because they're taking old machines and putting new chemicals in them.
Exactly. A plant owner has this expensive, massive piece of closed-loop dry cleaning equipment rated for solvent A, but due to environmental laws, they suddenly want to pump solvent B into it.
So what does this all mean? I mean, it's like trying to run a diesel engine on aviation fuel.
That is the perfect analogy.
Because converting these machines, you're taking a pressurized, closed system and repurposing it. The gaskets, the stress tolerances, the recovery condensers, the heating coils, they are mathematically rated for a specific fluid dynamic and chemical interaction.
Right down to the microscopic level.
So when you swap the solvent, you are invalidating the math of the entire closed loop.
You are. You're dealing with material compatibility. Take the elastomer seals on the pumps and the doors, for example.
Okay.
A seal made of Viton might be perfectly stable when exposed to a specific halocarbon. But if a technician swaps the machine over to a different hydrocarbon solvent, that same seal might swell up, degrade, and just fail within weeks.
Oh, wow. And what about the vapor recovery?
That's even worse. The vapor recovery systems are calibrated to the specific boiling point and condensation temperature of the original solvent. If the new solvent has a different thermal profile, the condenser simply won't capture the vapor.
And suddenly you have a highly explosive or toxic atmosphere bleeding into the workspace.
Exactly. Which is why the notes explicitly state that for the 2004 edition, additional guidance and definitions were added specifically to better define and explain these machine conversions.
They had to provide a rigorous framework for how to safely retro-engineer these systems. Or, I assume, forbid it entirely if the physics just didn't align.
Right. And that rigorous framework laid the groundwork for the 2007 edition, which fundamentally altered how engineers handle vapor concentrations.
This is where it gets crazy. The NFPA introduced options allowing a facility to increase the maximum concentration of vapors to 60% of the LEL.
The lower explosive limit.
Yeah. I mean, historically, fire marshals want you kept miles away from the LEL.
Yeah.
Like near zero.
Absolutely. Yeah. Near zero was the gold standard forever.
But the 2007 edition essentially says, if your redundant interlocks are fast enough, we will let you ride the Lightning right up to 60%.
Yes.
That is an incredible amount of trust placed in the electrical engineer's hands.
What's fascinating here is that it really marks the transition from blanket bans to performance-based design.
Okay, unpack performance-based design.
So The standard referenced NFPA 69, which is the standard on explosion prevention systems. The committee recognized that demanding near-zero vapor concentrations was just becoming operationally and economically unfeasible for certain high-throughput facilities using these newer solvents.
They couldn't dry the clothes fast enough. They had to clear every last molecule of vapor.
Exactly, so they offered a compromise. You can operate closer to the danger zone, gaining all that operational efficiency, if you can mathematically prove your autonomous safety architecture is flawless.
Wow. So if the concentration hits 60.1%, the human operator is irrelevant at that point.
Completely irrelevant. Human reaction time is way too slow.
The sensors must instantly kill the power, trigger emergency floor suite ventilation, or flood the system with inert gas.
Milliseconds.
So you are just designing an exhaust fan anymore. You are designing an autonomous life safety system with zero margin for latency.
Right. The sensor calibration, the placement of the sniffers based on the specific gravity of the vapor, the fail-safe states of the relays, all of that falls squarely on the facility designer.
That's a huge burden.
And 2007 introduced another massive engineering hurdle: requirements for dry cleaning, using non-flammable liquefied gases in pressure vessels.
Liquid carbon dioxide dry cleaning.
Yes. And I totally geek out over this part. Liquid CO2 completely upends the traditional hazard profile.
Because CO2 isn't a liquid naturally.
Right. Carbon dioxide is a gas at room temperature and normal atmospheric pressure. To use it as a liquid solvent, you have to operate at supercritical or near supercritical pressures.
How high of a pressure are we talking?
We are talking about operating pressures ranging from 700 to over 1,000 pounds per square inch.
That is insane. I mean, for 70 years, the facility designer's main hazard was just managing liquid spills in a trough or maybe some explosive vapors in the ductwork.
And now you are managing high-pressure gas systems. You are intercepting with the ASME boiler and pressure vessel code.
So the physical hazards change completely. It goes from flammability and toxicity to catastrophic kinetic energy and what? Extreme cold.
Extreme cold. If a pressure vessel fails, or even if a relief valve vents improperly, you are dealing with rapid decompression.
Which causes freezing.
Yes. Through the Joule-Thomson effect, the rapidly expanding CO2 gas drops in temperature dramatically. It can instantly freeze valves open. It can cause severe frostbite to operators.
And it displaces the oxygen.
Instantly. It displaces all the oxygen in the room, creating an immediate asphyxiation hazard.
So the architectural requirements shift instantly for the engineer. You need cryogenic storage logistics.
Yep.
You need pressure relief lines piped safely to the exterior of the building, and you have to account for the massive volume expansion of the gas when it exits the pipe.
The skill set required to design a facility expanded from standard industrial plumbing to hardcore high-pressure gas management.
And just to complicate the spatial layout even further, the 2007 edition also added a chapter for regular laundry equipment operating inside dry cleaning plants.
Yeah, that was a big shift in the industry model.
Right, because facilities were no longer these single-purpose chemical processing plants. They were becoming hybrid garment care hubs. As a designer, you now have to zone a single facility for entirely different operational risks. You have high-pressure CO2 or combustible hydrocarbons over here, and then industrial hot water washing and massive gas-fired dryers on the other side of the room.
And that spatial proximity of different hazards is exactly what forced the next major era of the standard.
Moving into the 2011 and 2016 revisions.
Right. The NFPA realized that their older blanket rules were actively penalizing new, safer technologies by forcing them to adhere to legacy architectural constraints.
So starting in 2011, they introduced definitions for wet cleaning and revised the definition of Class 4 solvents.
Which is important because wet cleaning uses computer-controlled machines with water and specialized detergents to process garments that previously required dry cleaning.
So it removes the volatile solvent entirely, but it introduces heavy commercial extraction equipment.
Exactly.
But here's where it gets really interesting. The most vivid engineering detail from 2011 was the revision regarding temperature control for laundry dryers.
Oh, the cool-down period.
Yes. The code explicitly mandated accommodating a cool-down period to eliminate the potential for spontaneous combustion. That is a terrifying phrase.
It really is. Spontaneous combustion in commercial laundry is a prime example of an invisible chemical hazard manifesting as a thermal event.
How does that actually happen?
It happens frequently with commercial linens, think towels from spas, restaurants, or industrial applications. These textiles retain trace amounts of unsaponifiable oils.
Like massage oils or cooking grease.
Exactly. Things the wash cycle doesn't fully remove. And when subjected to the high heat of a commercial gas dryer, those residual oils undergo oxidation.
And oxidation is an exothermic reaction.
Right, it produces its own heat. Now, while the dryer is tumbling and the blower is running, that heat is exhausted out of the building safely.
But what if the cycle ends and the clothes just sit there?
That's the danger. If a massive, tightly packed pile of hot textiles sits stationary in the drum, the thermal dynamics change. The heat from the ongoing oxidation cannot escape the insulating mass of all those fabrics.
Wow. So the temperature inside the pile just continues to rise on its own.
Yes, it creates a thermal runaway effect until it reaches the autoignition temperature of the cotton or the oil residue. The pile literally bursts into flames hours after the machine was turned off.
Hours later, the shop could be closed and empty.
Exactly. It happens all the time.
So by mandating a cool-down period, the standard dictates a hard engineering control.
Right. The machine's programming must continue to tumble the load while pulling in unheated ambient air.
Forcing the dissipation of that thermal energy down to a safe baseline before the door unlocks or the cycle fully terminates.
It is a simple mechanical solution to a very complex thermodynamic problem.
But the real structural revolution for facility designers happened in the 2016 edition.
Oh, absolutely. 2016 was huge.
The notes describe a significant reorganization that established requirements based on two intersecting variables: the class of solvent and the type of equipment.
They defined 4 versions of equipment, versions I through 4.
So prior to 2016, the standard was still carrying all that heavy architectural baggage of the 1950s and 60s, right?
Yes. The rules were written assuming you're using highly volatile chemicals in relatively open, unmonitored machines.
Meaning, if an owner bought a state-of-the-art, hyper-safe, closed-loop machine using a high flashpoint solvent, the local fire marshal would still open the older NFPA code and force the engineer to build the facility to the safety constraints of a 1970s chemical plant.
Which was incredibly frustrating for engineers. You would be forced to specify expensive, explosion-proof electrical conduits, pour specialized spill containment trenches, and construct heavy-duty, fire-rated barrier walls that were entirely disproportionate to the actual risk of the modern setup.
Just burning money.
It was an economic drain on development, yeah.
So looking at this matrix equipment versions through 4V intersecting with the solvent classes, did the NFPA basically create a carrot and stick approach for facility design? I mean, this isn't just about safety engineering. It is an economic weapon.
It is exactly that.
They are essentially bribing developers to buy safer version 4 equipment by letting them save massive amounts of money on the architecture.
Yes, the 2016 edition formally decoupled the rules. It states explicitly that requirements are less stringent for facilities that use higher classes of solvents, meaning higher flash points, less volatile, and newer equipment with built-in autonomous fire protection features.
So if I specify version 4 equipment, which is highly automated, fully closed loop, and designed specifically for a safer solvent class, the code allows me to strip away those secondary architectural protections.
Exactly. You don't need the massive separation walls anymore. You can reduce the specialized fire suppression systems.
You gain spatial efficiency, which in commercial real estate is everything.
And you save the owner significant capital on construction.
But the Matrix also introduced a brutal enforcement mechanism to protect that architectural freedom, didn't it?
It had to. The 2016 edition placed strict prohibitions on using lower-class, more dangerous solvents in existing equipment that was designed for higher classes.
So it closes the loop on that machine conversion hazard we talked about earlier.
Exactly. The NFPA recognized that you can design a perfectly safe, version 4 facility with minimal architectural barriers based on the initial specs.
But if the facility operator decides 5 years later to save money by secretly dumping a cheaper, highly volatile Class 2 solvent into a machine not rated for it,
the entire architectural safety net is gone. The facility literally becomes a bomb.
So to prevent that, the standard introduced a strict chain of custody for chemical safety. It requires that the authority having jurisdiction be notified for any changes in solvent class.
Yep. Even for changes within the same class, they added requirements to ensure chemical compatibility with the specific machine's seals and recovery systems.
And they also dragged the chemical manufacturers into the engineering loop, which is super smart.
That was a crucial addition.
The 2016 standard required the solvent manufacturer to certify the flash point and flammable limits of the solvent under the actual anticipated conditions of dry cleaning operations, not just in a sterile lab test.
That certification is vital for the design engineer. A generic material safety data sheet just gives you parameters at standard temperature and pressure.
Which doesn't help if the machine is boiling the liquid.
Right. A dry cleaning machine operates with heated solvents, pressurized sprayers, and heated recovery drums. The manufacturer has to certify how the chemical behaves under those specific kinetic and thermal conditions.
It gives the engineer certified empirical data to actually base their safety interlock modeling on.
Exactly. And that matrix of accountability brings us to the current blueprint, the 2021 edition.
Which is largely a refinement of that matrix, focusing heavily on usability and cognitive load for the designer.
They continued the reorganization they started in 2016, specifically targeting Chapter 6.
Yeah, the source notes indicate Chapter 6 now flows in a user-friendly way.
Yeah.
Requirements for the equipment and changes of equipment are grouped together, while requirements for the solvent and changes of solvent are grouped together separately.
Which sounds minor, but for an engineer actively working in CAD, dealing with cross-referencing electrical loads, plumbing layouts, and fire suppression matrices, cognitive load is a serious risk factor.
Oh, absolutely. A poorly structured code book leads to missed details.
Exactly. By logically bifurcating the hardware rules from the chemical rules, the NFPA really reduces the friction of compliance.
They also updated Chapter 4 to align flammable and combustible liquid classifications with their analogous solvent classification counterparts, right? Just standardizing the terminology across different engineering disciplines.
Right. It is the sterile, rigorous, bureaucratic work of maintaining a standard.
But, and I love this part, right at the beginning of this 2021 edition, amidst all the legal disclaimers and the solvent classifications, there's a sudden deviation into the human element. There's a dedication.
Yes. The technical committee dedicated the 2021 edition to the memory of James "Jimmy" DeSanto.
The text notes that Jimmy was a former committee member who grew up working in and eventually running his father's dry cleaning plant in Illinois.
He devoted his life to the industry, helping operators across the United States.
And it specifically mentions his passion for the industry, that he never met a stranger and always brought smiles and laughter to the room.
It really grounds the entire document. When you are calculating extraction volumes, specifying explosion-proof relays, or mapping out high-pressure gas lines, it is very easy to view these facilities purely as abstract industrial processing plants.
Right, just boxes with machines in them.
But you are designing for the Jimmy DeSantis of the world. These are not unpopulated server farms. They are generational family businesses.
People spend 12 hours a day, their entire working lives, inside the structural envelopes you design.
Exactly. The equations, the matrices, the interlock logic, it all ultimately translates into protecting human life from violent chemical physics.
So the code exists to ensure that the people who grew up in this industry can operate safely, even as the chemicals and the pressures become increasingly complex.
It's a heavy reality to carry into your next facility design.
It really is. I mean, we have tracked how the consensus process shifts the ultimate burden of independent judgment onto your shoulders as the engineer. We've seen how the standard evolved from mitigating the extreme baseline flammability of 1920s petroleum solvents.
Through the toxic complexities of the WWII-era halocarbons.
Right, to the intricate fluid dynamics of the millennium shift. We've explored how machine conversions and the introduction of supercritical carbon dioxide systems forced a whole new level of engineering rigor.
And that rigor birthed the 2016 matrix, which finally decoupled the legacy rules, allowing your advanced automated facility designs to benefit from reduced architectural burdens while still strictly policing chemical substitutions.
But the trajectory of all these revisions leaves us with a final, unavoidable engineering reality.
What's that?
Well, the 2016 matrix recognized that technology had outpaced the old rules, which required the creation of equipment versions I through feet. But the technology hasn't stopped.
Oh, not at all. Right now, facilities are looking at AI-driven automation, robotics that load and unload garments without any human intervention, and entirely novel chemical structures that haven't even been classified by the NFPA yet.
The code doesn't invent the future. It is entirely reactionary.
You, the engineer, are essentially writing the rough draft for the next iteration of the standard.
Your designs today dictate what the code must adapt to tomorrow.
The code simply scrambles to catch up to the physical frontier you are pushing.
So the question for you to mull over as you open your CAD software tomorrow is this. What engineering innovation are you putting into your current facility design that will force the NFPA to write an equipment version V?
Because it's coming.
It definitely is. You started this process hoping the standard would just give you the clean mathematical answers. But in the highly volatile, evolving landscape of facility design, you are the one building the bridge. Thank you for joining us on this deep dive into the blueprint of your industry.